Thank you, everybody, for joining us today. We will be going into the webinar now, which is the benefits of ONYX oscillators for LEO space applications. Thank you for joining us here on the 15th of November. As Bailey mentioned, my name is Michael Glass. I'm the RF sales engineer, one of the RF sales engineers here at ONYX Wenzel. I've also been joined by Patrick Mullen, who's one of our senior RF engineers. We'll be here to answer questions. We're going to tell you a little bit about who ONYX Wenzel is, where we've come from, a little bit of an understanding of the LEO space environment, how we'll be introducing the ONYX oscillators, and describe to you in some detail how we've adapted the ONYX oscillators to be used for LEO space applications. We'll be talking about the differences in qualification and test standards for a traditional, fully space qualified module as opposed to a COTS for space application. We'll also be talking about future trends in space technology, and then we'll be wrapping up with the Q&A sessions and a few key takeaways. We'll start by talking about introducing ONYX Wenzel as a company. ONYX Wenzel was started in 1978 by Charlie Wenzel and Liz Ronchetti, where we began by setting the standard for ultra-low phase noise performance in OCXO ovenized crystal oscillators. The oscillators that we started with were HF between 5 and 10 megahertz, and they were industry leading from day one. We have since branched out to be manufacturing custom IMAs, integrated microwave assemblies, as well as instruments. We do have fully space qualified range of products as well, but a majority of our products are traditional ground-based OCXOs. We also have integrated rubidiums into our OCXO products, and we also do custom assemblies such as VPXs and custom assemblies for our different customers. We have a long history of working and manufacturing products for space. Our space heritage goes back to 1996. One of our first launches was the Near Shoemaker satellite in 1996. As you can see here, we've also done several deep space applications and programs, including several of the Mars landers, the Mars Perseverance, the Mars Curiosity lander, and some of the new systems that we're on and working on right now. There's the JPL Europa Clipper, which is going to be going to the Europa moon, and that's scheduled to be launched in October of 2024, as well as the JPL Mass Change Measurement System, which was recently awarded to ONYX Wenzel and is in current development. So getting a brief understanding of the LEO space environment. LEO, or low Earth orbit space environment, is a region of space which is basically 100 miles to 1,250 miles up from the Earth's surface. This is defined as anything with an orbital period of 128 minutes or less. This area is obviously closer in than a geostationary orbit, and it is inside the Van Allen radiation belt. This is actually the most dominant area for the space vehicles which have been launched to this date. And as a consequence, it's a very crowded area. This is also the area where most crewed system flights have gone. This includes the ISS. And actually, no manned flights have gone outside of this range since 1972, the last mission to the moon. So the LEO space economy, this is kind of an indication of all the different applications and uses that are being found in the LEO environment. So in the LEO region, you can find uses in communication, in defense, research and development, commerce for communication as well, and then manufacturing and tourism. These are all aspects of the LEO space economy. So when looking at applications in the LEO environment, there are obviously benefits of looking at COTS for a space application in the LEO range or orbital area. For instance, you can tell the low energy threshold for placement. Obviously, being closer to the Earth, it's not as monetarily difficult to get into this area. It's obviously easier to get to because of its proximity to the Earth. You do have superior bandwidth and latency improvements because you are closer. There is greater flexibility in the orbital path and speed, simply because something like a geostationary orbit requires a very specific distance from the Earth. You have lower cost and shorter lead times, simply because it is closer and easier to achieve. And many of the customers and manufacturers are finding that the higher volume and manufacturability is available for this area. But you still have some of the challenges which are found in any space application. This includes resolving issues with vacuum pressure, radiation exposure, thermal variations from the dark to the light side of the Earth, space debris and handling that in that harsh environment. And also dealing with orbital decay and also dealing with a smaller field of view. So Wenzel has been manufacturing the ONYX oscillators. Our ONYX oscillator product range is a 1 inch by 1 inch by ½ inch profile sealed steel can. They were introduced in the late 2000s. The current version, ONYX 4, is small, lightweight, and ruggedized. It is considered a COTS or commercial off-the-shelf solution. Our ground-based and air-based applications, we have shipped more than 10,000 units so far. These are used in military tactical radios, airborne ground and shipboard applications, test and measurement equipment, synthesizers, base stations, as well as portable transceivers. These are used either in backpack applications, battery powered, or in instrumentation systems as well. The ONYXs have key features as indicated here. They are both HF and VHF oscillators, anywhere from 10 megahertz up to 300 megahertz. They have excellent phase noise, some of the best in the industry. We have low G sensitivity options available so that they can be used in rugged environments without degradation due to vibration. The outputs can be either sine wave or TTL. And they have a relatively low power consumption relative to their size and performance. All of the ONYX oscillators are manufactured with PCB through-hole mounting assemblies, and they can run over a wide temperature range from anywhere -40 to +85 degrees Celsius. ONYXs have been used and continue to be used in LEO space applications. The ONYX is an excellent candidate for LEO space because of its low size, weight, and power, and also it's a very low cost unit, but it's still maintaining very low phase noise performance. They're environmentally sealed and tested under a vacuum. They are radiation tolerant and have been tested as indicated in the future slide here. And they're used for anything in space, as you can see on the slide, including position, navigation, and timing, data transmission, space traffic management, data collection and validation, as well as security and defense operations. So when we are investigating using ONYXs for space applications in LEO environments, we started to look at what we needed to do to make them usable and to perform to the customer's requirements. So we started adapting the ONYX oscillators for space. We started looking at the traditional lot-based component level qualification, which would be standard for a space level, fully space qualified oscillator. And we started looking to see what we could do to design at the assembly level for qualification. And so we took a proven design, which was the ONYX, and we started looking at qualification at the module level. We started looking at the component ratings at the subassembly level, including transistors and passives. and making sure that they had adequate derating per the manufacturer's specifications for a harsh environment. We also tried to determine the best use for the radiation tolerance by looking at historical data as well as active test. We also provided vacuum pressure testing and continue to do so at the full assembly level. We also investigated our circuit layout to optimize thermal pathways and to make sure that the performance in a vacuum environment and temperature extremes could be handled and the performance could be sustained. They also use the solder sealed steel can, which is excellent for providing resistance against a vacuum. And we do full gross leak testing for a lot of our oscillators that are used for space applications. So as identified, there's obviously some component trade-offs, which is not unusual or not to be too surprising. When you look at the advantages, obviously they're going to be more cost effective. The cost of a COTS part is going to be much better than the cost of a fully space qualified using space qualified subassemblies and components. The availability and lead time is going to be much greater for a COTS part. There are technological advancements. For instance, the availability of high grade and high quality parts that have been space qualified is very limited. The amount of parts available is much better for COTS parts. It's easy to upgrade and to replace parts when they are COTS. And so we have easier upgradability for that. And of course, the lower swap C, as we've mentioned before. Our customers, when they look at buying a COTS for space part, obviously have to look at the trade-offs. There are some issues with potential issues with lot-to-lot consistency, reliability and longevity, and radiation vulnerability. These are issues which are identified by our customers, and the risk assessment is performed to guarantee that the performance necessary for the particular application is met. So comparing the qualification and standards of a traditional space oscillator versus a COTS for space type of module. The list provided here is probably only a short version of what could potentially be used for a fully space qualified module. Full space qualification standards are rigorous, and they ensure that the critical systems can perform reliably. You can see everything on the list from thermal vacuum testing, radiation testing, thermal cycling, environmental testing, part stress analysis. These are a lot of tests which are guaranteed and monitored by groups such as NIST, NASA, and JPL. And a lot of the test requirements are established and can be performed on a traditional space module. When taking those designs and modifying them for COTS for LEO space, qualification standards are pared down and are performed at the full assembly level. We continue to do full vibration and thermal vacuum testing. We do thermal shock, burn-in and electrical performance testing, gross leak testing. So basically, we're doing a lot of the testing that could be performed as a fully space qualified unit, but we're doing it at the final assembly level. We fully document and process all of our testing, and we have full qualification assurance and verification. We took a batch of our ONYX oscillators and have recently done a full radiation testing. This was performed by a third-party testing facility. They tested a 100 megahertz and a 10 megahertz ONYX. And the samples were powered and irradiated with a 50K rad sample dose. And for the TID testing, and the units were tested to be within the specified requirements before and after the testing. We also performed heavy ion and high energy proton testing. This can be performed to evaluate the ONYX response based on single event effects up to 200 megavolts. And so what I'm going to show now is some of the test results from these measurements performed. As you can see here, the blue line, which is the performance of the oscillator in phase noise from the control unit. So basically with no radiation application. And then the 5 different units were measured with 50 K-rads. All of these phase noise measurements were found to be within the specification, even after the radiation performance was tested. They were still considered premium performance as well. We also performed a full level of thermal vacuum testing on several different oscillators, both HF and VHF. The ones that are shown here are VHF oscillators. The ONYXs were solder sealed and leak tested, and then mounted to a fixture in a thermal vacuum chamber. The measurement was taken in 2 ways, as you can see here. On the top was a well-coupled ONYX to the thermal vacuum chamber. And then the picture at the bottom was non-coupled, so basically free air. In comparing those 2 oscillators, we could see a performance difference both in power consumption and in frequency stability and output power, or output RF power. The next few slides will go into that detail, showing the different temperature measurements from minus 41 degrees all the way up to plus 85 degrees Celsius. So in this first slide, you can see the red is a line indication of the temperature. The green is the non-coupled oscillator, and the blue is the fully coupled oscillator, well coupled. So you can see in this particular measurement, the frequency stability of a fully well-coupled oscillator is excellent. The oscillator performed quite well from a very cold temperature of minus 40 degrees all the way up to plus 80 degrees. You can see, however, that the non-coupled frequency oscillator does have a roll-off as the frequency shifts at higher temperatures. This is essentially when the oven disengaged, and the frequency did shift. The total shift, though, is, looking quick numbers, less than 2 parts per million, which for some applications might actually be acceptable. This is the next chart we're showing here. This is the performance of output RF power over temperature. So the same line for the temperature and showing the output power. The well-coupled and the non-coupled RF output powers performed quite excellently within the performance of the requirement. And they shifted less than plus or minus 1 dBm across the full test temperature range. So finally, this is a measurement of the DC power consumption. You can see quite a difference between the 2 different units, the well-coupled unit and the non-coupled unit. The non-coupled unit was quite flat in its performance of output DC consumption, as opposed to the well-coupled unit, which fluctuated from roughly 2.2 watts down to about a little less than half a watt, 0.45 watts. So as a manufacturer is looking to integrate an oscillator such as this, what could be gleaned from this is that as the design decision is made whether to choose a well-coupled design or a non-coupled design, the trade-offs in frequency accuracy, RF power, and power consumption can be selected based on the design what's the word I'm looking for? Integration, the design integration, sorry. So best practices for integration and production, as I just mentioned, the design can be qualified and assembly screen tested at the full assembly level for the most robust and reliable production. We can provide complete build packages with documentation. Bulk procurements and volume assembly can be had with very low labor and manufacturing costs. An agile design can be used. Custom test stations and fixtures can be manufactured as well for the best quality assurance. I'm going to jump in real quick about future trends in space technology. So for quite a while now, a lot of the customers have been asking for a new style of space qualification. And NASA has been leading the way with the NASA Electronics Parts and Packaging Program, or NEPP. This is something that was developed by NASA, and they're working together with parts manufacturers at the phase 1 and phase 2 levels to identify and qualify parts that are commercial, which can be established as established COTS parts. So these parts which have high volume and automated production facilities, and they can provide documented proof of technology and process, can be qualified as commercial parts, which are established COTS parts and can be better used and can be relied upon for COTS for space. The goal at NASA is to educate for best decision-making on what products are viable. As you can see here, you take a subset of all parts manufacturers, you look at the ILPMs, or industry-leading parts manufacturer parts, and then you look at the established COTS parts, which are within that subset of that subset. These are better screened parts and are more reliable. So as we've kind of identified, there are some emerging technologies in LEO applications. This is kind of a rehash, but basically you can see global broadband internet coverage, high resolution imaging, SAR applications, GNSS receiver experiments, and environmental monitoring and forecasting. Many applications are being used in the LEO environment. So what are we doing here at Wenzel for technologies in LEO space? Well, we've already started working on our modular COTS designs, including the ONYX. We're looking at other expanding that frequency solution catalog by introducing modular COTS for space systems that would include PLL systems, phase-locked oscillators, multipliers, and 1 PPS locking frequency references. So our transition is from a single oscillator as a COTS solution for space and moving to COTS solutions in a modular system. And so we're starting to integrate those system-based modular architectures for future designs. So again, just a little bit of a summary. The ONYX oscillators fit into future missions. Again, position, navigation, and timing. Oscillators which have low phase noise are excellent for PNT applications. Communications for multiple high volume constellations within the industry, both military and defense applications as well, scientific research, and commerce and entertainment. So with that, we've come to the end of our slideshow, and I'd like to ask if we have any questions. I'm going to bring this up to Patrick, who has been moderating and looking at the chat. And if anybody has any questions, to let us know. And if there are any questions, we'd be glad to answer them. Patrick's here in the room with me, and do you see any chat questions?
Yes, I am. I think we may be having a technical issue with the chat. Give us just one moment, please.
James Stewart, I think you had a question if you want to unmute. or if you want to enter it in the chat or Q&A at the bottom.
We got a Q&A question. So from William, we have, if you had to spitball an approximate percentage of cost savings on your ONYX COTS for space parts versus traditional custom full space qual parts, what would you say? 10, 20, 30% saved. I think the answer to that is going to depend on the customer. So in both the COTS for LEO and the traditional space environments, the costs can range quite wildly depending on the application the customer is using it for. So if we have customers that are doing things for geosynchronous, traditional space, that may run in the tens of thousands of dollars. For some of our interplanetary missions, those can be $1 million traditional space parts. For those, for our COTS for LEO, depending on the customer, if they are doing low cost, if it's a university or a small startup who's just sending up some CubeSats, then they may essentially be buying a almost COTS part with very little additional screening, just with the understanding that the design has been qualified for use in that environment. We have other customers who are doing LEO applications, but they may have $1 million satellites with $1 million launch costs. And in those applications, they may need further screening to make sure that the critical oscillator that allows the satellite to function is going to work and survive launch and have their $1 million satellite function. So generally, I would say it's usually something like an 80% cost savings, but it does depend on the market that the customer is asking us for. We provide cost solutions for each of those. To the anonymous attendee, have you supplied your products with the SpaceX program? I don't believe we can discuss our particular customers, but we have supplied our ONYXs to companies intending to do low Earth
Applications in
orbit,
space.
yes, low Earth orbit internet providers.
Several.
Yes.
Yeah.
Anyone else have any questions? Can you discuss the implications of non-standardized or non-qualified timing components in LEO missions? What are the risks associated with using components that do not meet established standards, and how can these risks be mitigated? So this is something we discussed somewhat in the slides, but to go a little more into it, again, it depends on the customer's requirements. For most of our customers, the oscillator is a critical component of the satellite. If the oscillator has a failure, the satellite is non-functional. So this is something that our customers care deeply about, knowing that this will continue to work. It's a critical application for them. As we mentioned, some of it is buying COTS parts from manufacturers that we trust, industry leaders like the ones as detailed in NASA's documents that have proven their reliability and repeatability from batch to batch of the components. Some of that is the design effort on our end, making sure that the design does not open us up to any sort of single failures or latching that can take place in a radiation environment. And finally, it's screening at the parts level to make sure that our manufacturability, solder joints, things along those lines are ready for space. So that includes things like burn-in testing to get rid of infant mortality and thermal shock to assess the health of all the manufacturing. Okay, so another anonymous attendee. For the uncoupled tests, was your DC power consumption constant and relatively low through the thermal transition? Is this due to the oven going to its lowest settings since the internals are hot and uncoupled? Yes, that is fairly accurate. So to look at the graph, essentially, for the uncoupled oscillator in a vacuum environment, essentially the only heat transfer mechanism is through the pins and through radiation. And so as you can see, even when the temperature is still at in the extremely low ambient range, -40 to -20, the green, spike, if you will, on this scale is the oven turning on at 2.5 watts, which is the standard for both units. And then almost immediately, the internals warm up to the full oven temperature, and then the oven requires much, much less power to maintain that internal oven temperature. So that's why it immediately drops to 0.6, 0.7 watts, because very little power is needed to maintain that temperature. If we were to zoom in on the scale, we would see similar steps in the wattage to what we see on the well-coupled blue line. But the scale is so small, it looks essentially flat compared to the initial warm-up power. For some customers, if they are in a satellite system and their thermal engineers have said, we are going to be primarily in the lower ambient range, we have a robust thermal control system, this may be a fantastic solution for them, because essentially they get very little heating. They have very little power draw from the oscillator, which also means that there's very little heating of their surrounding parts. Everything in the satellite is interconnected, and if the ONYX is having to use a lot of watts to maintain its oven temperature, that is going to heat up parts around it. Now, for other customers, they may be controlling things at the higher ambient range or the full ambient range, and they need a solution that works over the entire range. For that, we would suggest the coupled output, the coupled ONYX, because while it does use more watts, the watts it uses are very similar to how the ONYX performs in an ambient air environment. And that is something we have a lot of history with. We know that over that full temperature range, the ONYX is rugged and reliable for a long lifespan. And if you're at those higher ambient temperatures, then even the well-coupled ONYX is not drawing as much power. It's down to less than a watt. And in these satellite systems, less than a watt is not a significant factor for them.
So the customer can kind of tailor fit their application based on how they install it,
Correct.
whether it's well coupled or non-coupled.
Correct, and that is something we work with our customers on, because while the method the customer uses to mount our ONYXs always has an impact to some degree on the DC power consumption and similar characteristics, in a space environment without air around it, how the customer chooses to mount it becomes an even more important decision. And so we work with our customers to understand their system, their temperature environments, and their power needs to pick the correct coupling mechanism for their system.
Thank you, Patrick.
Mm-hmm.
Have we seen any other questions come in? Does anybody have any other questions or comments?
Okay. I think if there are not any more questions or comments, then we can give everybody back some time. If there are any follow-up questions, I encourage people to reach out to Michael and Patrick via quanticwenzel.com and to join us next month in December for the next webinar, which will take place on the 20th of December. For more information, you can go to quanticnow.com/thegrid. Thanks, everybody, and have a great day.
Thank you.